We're going to be looking at the Lufilian arc. Can you see that? Yeah. Lufilian arc up there. And the lake stage foreland basin, the upper Kundalungu, that's the upper part of the Katangan succession. In the Damara, we're going to be looking at that, but we're going to be looking at the northern platform of the Damara. Sorry, I'm pressing the wrong button. That's the northern platform, the deep blue. It's got the whole Damara succession there, and that's where a lot of our copper is. That's the boundary fault, the edge of the northern platform. That's the main Damara origin, the high temperature origin, and I'm going to be taking information from up here and in the main origin and a little bit down on the southern foreland as well. And by the same token in Zambia, I'm going to be taking information from the Lufilian arc, but also from the equivalent Zambezi belt. The boundary in Zambia between the two is the Wembweshi shear zone. Right, very simple stratigraphy to start off with. Those two sequences, the Katangan and the Damara northern platform succession, have basically always been equated with each other simply because they have a lot of carbonates. And there are arcoses, feldspathic sandstones at the base of each. But what helps that correlation is we have two snowball earth glacial units, the Churs and the Grand Conglomerate, the Gulp and the Petit Conglomerate. What strengthens that is this, okay, this microphone. Okay, nobody's saying anything. What strengthens that correlation is those units have identical cap carbonates. So the Churs has a grey cap carbonate, so does the Grand Conglomerate. The Petit has a pink or tan cap carbonate, so does the Gulp. The Nosset group, our basal unit, rift phase, intracontinental rifting. On the northern platform where we're going to be looking mainly, about a kilometre thick up to 1.2 kilometres. In Zambia, the lower Rhone, at its thickest, a kilometre thick, often down to 200 metres, even not there. In Namibia, at the top of the succession, at the end of that rift phase, we have the alkali volcanics, the Nauport volcanics, right up against the boundary fault of the northern rift. And those are the ones that I didn't recognize initially, all igneous rocks. Okay, I'm going to give you some names now. You don't need to remember them at the moment, but key things are the Beersfluchter Formation and the Kitwe subgroup. And within the Kitwe subgroup, you have the ore shale member. And most of the deposits in Zambia occur within about 200 meters of the ore shale member. We're going to be looking a little bit later at the Ukukuyu Formation and the Mwashi. We're going to look at the glacial units, we're going to look at a little bit at the Habanab, and we're going to look at the Gulp, we're going to look at the Tsumeb subgroup, and then the New. And we're going to start by trying to match up the ages from the two regions. Now, in Namibia, we don't know what the age of the base of the Nosset is. Now, I've taken the data from Zambia and assumed it's equivalent, the same age applies in Namibia. It's a guess, 883 million years in Changa granite. And the lower Rhone rests directly on that. It fits, it seems to make sense, that age. As the beginning of Arcose deposition. Now, those are essentially red beds, pinkish units. That's the lower Nosset in Namibia. Pinkish Arcoses or feldspathic sandstones. I have no photograph from Zambia, But that is in the DRC, and a lot of photographs. Murray Hitzman has kindly provided me with a lot of photographs. The old Belgian geologists actually had very useful terms. They didn't use formation this and formation that. They described the rocks by what they saw in them. So that was a rock with an argillaceous rock with talc in it, the red. So it's a fairly fine-grained rock in the DRC. We don't have any ages within our Nosset. We know that our Nosset finds upwards. The lower Rhone arcoses fine upwards. There is the Rushinga complex in the Zambezi belt, 804 million years, so it's within the ballpark. This is why. The Nowport volcanics, they come out, those volcanics top of the Nosset, they come out at about 752. So that seems okay. It's within the Nosset age. Those are the Nowport volcanoes. Pyroclastics, per-alkaline ignimbrites. 6.6 kilometers thick, we don't see the base. That's in two big dome structures. But associated with them is a nepheline cyanide, the other cyanide. It's the Loftar nepheline cyanide. There's a huge swarm of sulfide carbonatite dikes, and we're going to come back to that. Those have high xenotime, high yttrium, and rare earths. We'll come back to that later. They're phonolite dikes as well. Our northern rift, that whole zone there is the northern rift. It is very deep. It's got 17 kilometers of Damara sediments in that rift. And generally we don't see what's at the bottom, what the rift section consisted of. But at the top of the Nosset, in that area, at that point there, Okanjandi graphite. There's a graphite deposit that's an archive full of graphite. It stands up against the marbles on top. And I believe that's a cooked up oil deposit. In other words, we had saprophytic shales deep down underneath in that rift. On some of the thrusts, there's evidence that we also had evaporite stone. They come up with thrusts as an intrusive brown dolomites with albetalite, fragments of albetalite that we get on a southern margin of evaporite. Albite, fine grained, chert-like rocks, about 80% albite. Okay, we're going to come sometime back to our southern Nosset Rift. That is now down there. I think it used to be here, and with continental breakup, that's the Kalahari Craton and the Congo Craton up there, starting there. Not everybody believes it starts there. Some people believe it starts there, but I think it starts there. And that with continental breakup, that southern rift that used to be here has moved southward. It is now in the southern margin zone. The southern rift, evaporites, feldspars, pseudomorphs after evaporitic minerals, tenadite, pseudomorphs after gypsum. In places there's a lot of scapolite, in other words, high chlorine, and here and there we'll get laminated tourmalinites after boron, hot springs, boron exhalations. Okay, going up. There are some volcanics in the lowest of the carbonate units. All the carbonate units are in blue. 759, 746. There is a basalt in the lower Rhone, in the upper Rhone, 764. I'm not sure how good that age is, but it's not too far away from those ages. And the key thing in Namibia that we need to look at is the lower Beersflugter formation. That unit down there. It's the equivalent of the copper belt ore body member up north, at the very base of the carbonate succession. And careful mapping in the Kalkveld has shown that it's actually a tectonic displacement unit wherever there are phyllites, and it consists mainly of phyllite. There's some upward shallowing with an exposure surface as well. So we need to be looking, and we have been looking, at the Beesflugter Formation. The deformed ore shale member in the Mandela mine in Zambia, and you can see the deformation in there. So that too, at that level where you get most of your mineralization or close to it, there is deformation, dislocation. All right. In the Kalkveld, the carbonates interbedded with those phyllites have the dark bands in here are chert bands. Now I'm pointing that out very specifically because we're going to come back to that later. What are those chert bands, or what were they initially? Drilling of the Beesflugter Formation, talc biotite phyllite. Is that after anhydrite? No, uncertain. But the important thing is a lot of talc there, certainly in places. There's also in the Beesflugter Formation, remember this is where we get a lot of the copper in Zambia. We have calcareous pyritic sandstone. In other words, the pyrite is a potential reductant. Black shales are potential reductants. There are also stromatolites in the carbonates in that lower unit. Organic activity, potential reductants as well. Right? Some of Murray Hetzman's slides. That is the lower Rhone, and that's the upper Rhone up to there. The SAG phase, he calls it, continuation of evaporitic siltstone, mudflat deposition, shale with grit, facies interlaid with extensive evaporitic platform carbonates, greater than 600 meters thick, up there. Evaporitic thickness not as unknown, anhydrite abundant, widespread voluminous brecciation. Halokinesis indicates evaporite movement and late salt dissolution. In other words, salt that was there is dissolved out and gone, and what remains is a brecciated rock. Okay? That's where we are in the DRC stratigraphy, the D-strat. Dolomie stratigraphy. Again, the Belgian term, a banded dolomite, simple name, banded algal carbonate. And again, the term algal is coming out again. Dolomite and magnesite. Decreasing magnesium alteration, talc and magnesite away from that underlying rat. The rat with the red beds underneath. Are the red beds underneath? The next units, laterally equivalent, RSF. It's a ferruginized Felicity, silicious rock, Komodo dolomite formation, originally an evaporitic dolostone, and it's now highly silicified. And that seems to be an important feature. A little bit higher up in the sequence, RSC. Abundant domal stromatolites, significant gypsum. So we're very shallow. We're in the photic zone, and it looks like there was often exposure to give us the evaporitic minerals. We go up in our sequence in Namibia, the Davida Formation, cycles of transgression, and then shallowing upwards and final exposure. Shallowing upwards and exposure. Potential for obviously stromatolites, organic activity, and and exposure surface therefore evaporates. The next unit up, dolomitic shales, laminated mildly carbonaceous, dollar siltstone with some relic evaporites. We're still talking evaporites in the DRC, major flooding surfaces. So there seem to be a number of depositional cycles within that succession. And then dolomite with black minerals. Dominantly pale to dark coloured bedded dolomite with several prominent chert horizons after evaporites. That's Murray's comment, chert horizons after evaporites. That's his interpretation of the evaporites, or the chert singular. The upper Rhone, sag phase, evaporitic siltstone, evaporitic platform carbonates, and anhydrite abundant. And those are the minor cycles up in that unit in the Zambian copper belt. Cycles up to 2 meters thick, they're shallowing upwards, non-evaporatic at the base, sandstone, siltstone, mixed carbonate, siliciclastic, and finally evaporitic anhydrite magnesite dolomite. Sequences become more evaporitic upsection. And higher up in the sequence, DSG, heterogeneous sequences of red siltstone, evaporatic dollarstones, abundant gypsum clasts, massive stromatolitic dollarstones. All those things could be important for mineral deposition. Okay, and then higher up altogether, limestones and dolomites, many stromatolitic, or with algal lamanites, in other words, organic activity. Minor silicified zones after evaporites. That's our upper unit, the Okapuyo Formation. Several transgressive units that shallow upwards. And here we have a difference between Namibia and Murray's interpretation in Zambia. There are our shallowing upward cycles of the Okapuyo, and possibly it's shallowing upwards, the whole basin is shallowing, because we possibly approaching that first snow earth glaciation. Right? Certainly towards the top we must be. Okay, in Zambia and Congo copper belt. Major flooding event, basin water, deposition currently of true marine sediments. Those things there, those black shales, fill-ups. And in the photic zone, the shallow zone, shallow prominent parts of the Zambia copper belt to deep water marine, common in Congo copper belt. Now, I have a problem with that. If in the Damara we're shallowing upwards as we're approaching the truest glaciation, that surely can't be a marine transgression. I think what that is we probably have half grounds and isolated basins, deep basins within those half grounds. Don't know how extensive that unit is actually. But that doesn't matter, that's fine. That's black shape, potential reduction. There are also gabros in the succession in Zambia. Ages from 765, in other words, near Tectonic, to 740. They predate the Chures, but they also occur up into the Grand Conglomerate. But the Grand Conglomerate is deformed, and they may have been tectonically emplaced into the Grand Conglomerate. We get to the age of the Grand Conglomerate, 717 to 659. None of that comes from Africa. That's from elsewhere in the world, where it has Sturgeon snowball glacial units. There are porphyries in the Grand Conglomerate that have been dated at 735 by Roger Key, plus or minus 5, but they're described as ponds. There's iron formation, also described as poles. And from their description, they sound like they're tectonically impressed, because that is older than anything we have for the age of the Stratigraphic horizon. Okay, the chores in Namibia. Sorry, ground moraine, sturdy and snowball earth. You also get, George Henry will recognize that photograph, down in the deep water, in the central Damara, turbidites with drop stones in the pelagic tops of those turbidite layers. There are many places where it's very hard to tell what kind of rock that was, and I think a lot of the units, especially in the deeper water, are actually mass flowed units, and often the pebbles, despite the deformation, the pebbles are orientated as if they've been orientated by mass flow. You also get iron formation in Namibia. Generally, the iron formation does not have clasts in it. This one has deformed clasts of dolomite, yellow dolomite. That iron formation is being looked at, is looked at in the past. Generally about 34% iron, 4% manganese, depends where you are, magnetite, hematite. Places where you can actually see drop stones in the iron formation. It's not common. And that's the grand conglomerate in Zambia. Right, we get up into our cap carbonates. Remember, and in Namibia we always used our glacial units as our marking units. But we've had a huge sea level change. Right? So the glacial deposits are actually polyphonic. They're not a continuous horizon. Once the ice melts, you have a tremendous transgression. That is our marking unit. And we can map out where the choose formation used to be simply by mapping out our market, our transgressive, our cap carbonate. In Namibia, that's what the choice cap carbonate looks like, laminated, grey to dark grey mollusca. In the photic zone, you also have algal laminites. Despite the fact that we've come out of a glaciation, there is algal activity almost immediately in the photic zone. There's a fine algal laminites in there, and sometimes a slumping of those laminites so that you get the roll-up structures. Off into the deeper water, that's the southern edge of the northern the Transmontane Ridge, in water depths of 500 to 800 meters, in the right. Dolomite, turbidites, and one layer after the other is they're identical to each other. Typically called rhythmites. Rhythmites can be a millimeter thick, they can be a meter thick. As long as they're identical like that to each other, they're called rhythmites. In Zambia, same unit, some banding. In DRC, it's often called the Dolomiticri. There's a very fine banding. In the southern margin of the Damara, we get the Gubavis member, which is the cap carbonate to the chores. There's no chores there. But you can see how it could get the name Dolomiticri. The next unit up, the Gauss Formation in the Carbonate. Most of that formation is a breccia. And the breccia fragments are surrounded by isopachous dolomite cement. That's what it looks like, with silicification on either side of those cement covering. And close up, there's your isopachous cement ground fragment and the silicic edges to that isopachous cement. What is that silica mean? What is that silica mean? We're going to come back to that. Going up in the sequence, Grace Formation, just before we get to the next snowball earth glacial unit, Grace Formation, highly silicic with carbonate, microlaminite, subaerial TP structures. In other words, algal activity, exposure. Possible, what's the possibility of evaporites there? That's Namibia. Then we get up into the Gulf, the next snowball earth glacial unit. 635 comes from the Namibia, the very top of the Gulf Formation. 649 from elsewhere, no dates from Zambia, the conglomerate, but a much shorter glacial episode. That's what the Gulf looks like in the Otavi Mountain there, full of carbonate glass, because most of your succession underneath is carbonate, an abundant carbonate-rich matrix. In places along the Fransfontein Ridge, you have what could be a ground moraine, almost class supported. So it varies along strike. You also get what look like on the Fransfontein Ridge mass flows, one mass flow after another, into that deeper water where we had the rhythmites. There's a boundary, stratigraphic boundary in there, and there are rhythmites in there. You can see the banding, those rhythmites are better developed over here. There's even some down here. You notice that mixed-up was not steady. It's very seldom that we see grading before. Okay. Now we're at the top of the Gulf Formation, and there's its cap carbonate. The carbon, remember, a tan-coloured cap carbonate. That is our main marker unit. Again laminated, like the lower cap carbonate. And within that unit, where we're in the photic zone, straight after the melting of the ice, you get vertical stromatolite columns. Those stromatolite columns, which Paul Hoffman called plumbed stromatolites, because he believes they were vertical to bedding. And in between, the cavities in between, filled by dolomitrite. Now, it is rare to see the stromatolitic structure. What you normally see would be these pipe structures, those pipe structures. That's where the stromatolites would have been, or would be. You can't recognize it, but you see the pipe structures very, very easily. And you get that with the cap carbonate to that Marinoan glacial unit, identical cap carbonate in different parts of the world. That's what those pipe structures look like on plan. And there we are in Zambia. Fatigue conglomerate down there with a clast in it. Fatigue conglomerate here. And then the cap carbonate, which in the DRC is often called a Dolomie rose because it's slightly pink. Now remember, we had the oceans frozen to the coast. They had a massive sea level fall. But then we also had huge transpiration. There's our Kyle member. There's no glacial unit underneath there, but that's our marker unit. The succession up to there, 400 meters thick, the Myberg Formation, its first exposure surface is right up there, at the top of the Myberg Formation. So we have one sedimentary site, 400 meters thick. As we go upwards into the next stratigraphic unit now, on the seafloor of the Myberg Formation, there were crystal fans, sometimes that big, sometimes bigger, sometimes only about 2 centimeters high, of aragonite growing on the seafloor. It's now transformed to calcite. Remember that as we melt the ice, the sea is getting warmer, that absorbs the heat from the sun. You still have ice caps. You have tremendous temperature changes, so you have a vastly wild climate, and your wave base is very, very deep. So within the Myberg Formation, you get giant wave ripples in places. Okay, there's the Myberg Formation in the Otago Mountain. Up there, that whole thick unit. Up here somewhere, that first exposure surface, the top of the Myberg. But all those ridges in there are mass flow deposits, and that's what they look like. Potentially, mass flows, potentially fluid flow conduits. That's the next unit up in the stratigraphy. Lots of much shorter depositional cycles. The shales of transgression and slowly shallowing upwards, the next transgression shallowing upwards. Totally different sequence. The next unit up, the Huttenberg Formation, algal laminites. Again, organic activity. Okay, what we also have is at the top of the Huttenberg Formation, that's the top of the Otago platform carbonates, a lot of silicification, silicified oolite, and also silicified stromatolites, lots of them. What does the silicification mean? And near the bottom of the, not too far above the Gulf Formation, you have this nodular limestone. No, sorry, T7 is higher from the stratigraphy. T8 is the last unit in the Tsumeb subgroup. So T7 is higher from the stratigraphy. The strange structure, and it's been interpreted as the nodules are calcite replacing anhydrite. So evidence of some evaporates. At the combat mine, there are features that have been interpreted as chicken wire texture, calcite after anhydrite. In the same area, you have oolites that are black, probably with a fair amount of carbon in them. Oolites, shallow water, obviously. You also have those features, fenestrine, that are ascribed to gas escape of hydrocarbon gas. That's way down in the gas formation. Again, something like fenestrine structures in there is better on the other side of the specimen. But you get globules of bitumen as well. That was in the rock. Now we're going upward in the sequence. The top of our carbonate succession in the whole Damara. There it is up there. On the southern margin we have a rhyolite. It's been dated as 609. After that, in the central origin, but not up on the northern platform, we have a thick succession of grey rockies, the quiescent schist. So we're ending carbonate deposition throughout the origin at about 609. We don't know exactly when schist deposition stops. This is, we're in a spreading phase. We're separating the Kalahari craton from the Congo craton to the north. We've already developed ocean floor within the southern zone. 600. What gives strength to that date are the ages of the first metamorphic garments. 595 in the Congo Belt, 595 in Zambia. Deformation, first phase of uplift and erosion. The erosion products coming from the Congo Belt in the west, as well as from the Damara origin to the south of the northern platform. The northern platform is deformed by B1 deformation along its edges. So that is our northern Malats, the Morgan group. And I think the Upper Kundalungu in Zambia, which is described as the foreland basin deposit, is the same thing. They know very little about Kundalungu in Zambia because it has no copper, so they haven't looked at this detail. All right. We're looking at the Morgan. There's the Nosip group, the red beds underneath. There's our carbonate succession with the 2 glacial units in it, the Atavi group. And all that green and the red on top is our molding. And the key thing is, in this particular slide, is that uplift and unconformity at the base of the tube, at the base of the molding group. Around the edges of the northern platform, you have deep intermontane erosional basins. The Atavi carbonates are the light-colored units there and on the other side. This deep erosional valley is filled with molten sediment. And you get totally proximal sediments with no rounding at all of the fragments. And you get far more, in those intermontane basins, far more distal sediments, chlorite, muscovite, phyllites. Every intermontane basin has its own stratigraphy essentially. We're subducting the Kalahari craton, transpressive subduction of Kalahari craton in the northeasterly direction below the central zone of the origin, and of Africa in a northwesterly direction below South America. This is an active continental margin uplifted for the first time from about E1. So it is shedding sediment into the closing southern zone ocean. Some of that sediment gets right across onto the Nama foreland basin out there. The Nama, its base, has an age of about 555 million years. The detritomicas in the lower Nama succession, the foreland part of the Nama succession, have ages of 750 to 650. In other words, the early metamorphic ages of the South American craton and the central. Right. We get to continental collision of the Congo craton with the Kalahari craton. D3 deformation in the central zone. D3 granites, deformed granites 542. It's the end of the Ediacara period. In Zambia, the oldest granite, 551, not too far away. That is when we had collision. But it's also supported by what we see in the Nama. There is the sediment that Southern Zone Ocean had closed. So those active continental margin sediments were now transported right across the closed Southern Zone Ocean onto the foreland, and also from South America onto the foreland. And we see in the Nama succession there are ashes. The very top of the foreland basin succession, there's an ash with an age of 543 plus or minus 1. At the very base of the southern molasse, the red beds of the southern molasse, 539. There's an unconformity in the Nama, 4 million unconformity. That is the Cambrian, pre-Cambrian boundary. 542 is when we had continental collision. So those ashes support what's going on inside the Damara. Our oldest post-tectonic granite, 539. There's a rhyolite in Zambia, 538. Okay, a peak of regional metamorphism. In Namibia, 535, it post-dates the collision. 534, 535. The Enterprise nickel in Zambia is believed to be in place during metamorphism. So it has an age of about 540, but there are white mica, there are white schists in there. 530, that is dated at 530. With that peak of metamorphism, you had tremendous partial melting of the Damara, the pre-Damara basin. And it's a real dog's breakfast. You have some partial melting of the cover sequence. You even have a little bit of partial melting of the early syntectonic Damaran granites. Up north, the Nkuba group, the Kundulungu limestone, there's evidence again of evaporite with scapolite crystals, in other words, high chlorine. Those are the white schists from Zambia. White muscovite kyanite schist with chalcopyrite. Murray does not believe that means high pressure. Our post-metamorphic granite, the oldest post-peak metamorphic granite, Donkerhoek granite, 527, that's got its own thermal aureole that overprints the regional into paragenesis. Muscovite cooling through 500 degrees. In Namibia, depends where you are, 524 to 506. In Zambia, 510. Cooling through 300 degrees, biotite cooling, 460 to 465. Very, very similar. Okay, what does that all mean? Post-M2 mineralization during initial cooling from 530 to 510. Orogenic and platform fluids, high saline fluids carrying base metals, low saline carrying gold, and Great Lake mineralized granites. We're going to look at those a little bit because with continental collision things don't stop, they carry on. We're looking at the northern platform again. We're looking at the central origin. Okay, we have the detachment. Remember that detachment of the Beers Fluctor Formation. The same in the copper belt, ore body memory. We have mineralization in Namibia in the western part of the northern platform, at the bottom of the Nosip, in the middle of the Nosip, and there, near the bottom of the carbonate succession, just above the Nosip. There's the ore shale member. The Moana is at the bottom of the lower rock in Zambia. There, we're still in the pre-Jura succession here, so that in the carbonate there's also some mineralization in Namibia. There's the Nosip in Namibia, in the western part of the northern platform. The brown, light brown is the Nosip. The first unit above it, the light grey, is the Beers Fluctor Formation, and look at where all the mineralization occurs, all those fine dots. And not just above the Nosip. And that's just a blow-up of one of the prospects that was drilled. There's the Nosip, there's the Beers Fluctor Formation, and it's right in there. And on the other side, there's some mineralization in there too. So, ore shale member, Beers Fluctor Formation, both with mineralization. That's what the Beers Fluctor Formation phyllites look like with mineralization. They're very recessive and they don't outcrop well. And it's one reason why they've been missed a lot. Some of the units a little bit above the base, there's the Nosip contact, have mineralization all along for at least 800 meters. That mineralization, now this is from the Kalahari copper belt, but that mineralization is a problem. When was it in place? In the Kalahari copper belt, you get disseminated mineralization in zones that had a porosity in the siltstones. But you have cross-cutting veins as well. And there's another cross-cutting vein over there. That's just to illustrate disseminated mineralization. But in the Gulf belt, you get mineralization associated with quartz veins. You get mineralization associated with shear zones, with chalcopyrite, bornite, malachite, chrysocolla, shear zone in there. You get mineralization associated with fragmented, red shaded carbonates. And that's from some borehole core, the quartz vein, chalcocite, and malachite. In that Same area, they have drilled anhydrite, so the pink mineral is anhydrite. And the white mineral in that case is anhydrite in schists in that same lower sequence. Here's flux mineralization. Some is disseminated, the age is uncertain, but most of it is in post-folding veins and shear zones. We're going to see what the copper bit tells us about that. Right, coming back to our sequence on the northern platform, Nosset, Tabi group carbonates, and then the Moulden. And we're going to looking particularly at the Chewy formation. It's feldspathic sandstone. Often the lower schist is not there. Remember, I said the D1 deformation there was uplift, at least to the margins of the northern platform, and maybe more than that. So we have an unconformity at the top of the Atabi dolomites up there, with the Moulden resting on top of that Atabi. There's that thick feldspathic sandstone, the Chewy formation, right on that unconformity. Because we had exposure, there was also casting. Casting, in that case, on a small parasitic fold structure, the Tsumet. The feldspathic sandstone in yellow poured all the way down that open pipe to 1,700 meters below present exposure levels. The sand, that feldspathic sand, was the conduit for the mineralizing solution. That's largely the sand that is mineralized. There are fractures outside, as you can see in the carbonates. The combat mine, rather than being a fold structure and a pipe structure, that's casting along a series of joints and fractures. There's the sandstone, there's the mineralization. There is the orthosic sandstone, and that's mineralized. And the characteristic feature of this these polymetallic deposits, Summit type, is calcitic alteration. So that is calcite, and that's the original dolomite. It's a lot of calcite, the light grade is the original dolomite. And that's one way to recognize the polymetallic mineralization of the Tsumet type. We also have lead zinc mineralization. The Berg-Okas pipe. Up and up, there was a pipe, as well as stratiform unit. Berg-Okas has been drilled recently again. That is massive sphalerite, with the grey layers being galena in between, so much more galena up here. And with continental separation, breakup, the African erosion cycle, casting in the Atabi mountain land, fluids coming in, reacting with the sulfides, oxidizing them, and bringing in vanadium, so that you get zinc, lead, vanadium deposits in solution collapse bridges. That is typical of Berg-Okas. Then Branko Corner, ex-professor of geophysics from here, recognized in his PhD many years back that there were north-northwest trending lineaments, shear zones, and they're actually shear zones that rule shear zones. And they have a major influence on controlling where fluids, post-tectonic fluids, flow. Those are quartz veins, high temperature quartz veins, 525 million years, Novochok gold skarn deposit. The elastites tend to be similarly controlled by these north-northeast trending shear zones. The elasticite from Rossi, 350 ppm, mining up to 4,000 kilograms per annum, and they have about 30% secondary uranium minerals. The Ois tin mine. Those are tin crystals in there, cassiterite crystals. The grade was only 0.26%, but they were recovering with big James tables, banks of James tables, 88%. They're the dumps, and those dumps are being used today to make high quality bricks. All right. We're getting to what we need for mineralization. The Tambi Mountain have basement in pink, Nosip in the orange color, and you will notice that Nosip is not everywhere present. It looks like up there on the northern platform we certainly had half gold. Okay? So we're talking faulting and maybe quite a lot of faulting. That's Nosip in there, and all the rest is the Atawi carbonate succession, the dark green, the Mulden up there. There's Tsumeb, there's Combat. Those northeast trending features are not well developed here, and rather we have Combat a lot of northeast trending faults. Differences and similarities between the two regions. Near the Ruakana Falls, the northeastern edge of the northern platform, in the Nosip, that's about 1 kilometre thick, and plenty of carbonates underneath. That is where they have been looking for mineralization. The various exploration companies. Everything's correct there. Kitwe Formation, emergent evaporative classes, the evaporites, massive anhydrite, magnesite beds, the Andola antelope plastics up there. This is the top of the lower rock. There's Kitwe Formation. There's a copper belt ore body in there, very near the base. We go back to the DRC, the RSF. That was those initial dolomites, originally an evaporated dolostone. They are now highly silicified. And in some of the sandstones, you can still recognize the original shapes of the evaporated minerals. Going a little higher up, the RSC, those stromatolitic dolomites with evaporites in there. Early silicification of evaporite, and then multiple periods of silicification of dolomite growth. What does that mean? Getting higher up still. All right, the banded dolomite, better dolomite with prominent chert horizons after evaporites. That's the Inlandshoek formation, and above the Meyerberg, silica jasphalite. Just massive, these big bodies of silica. That's in the northern edge of the Tavi Valley. What do they mean? Where does all that silica come from? That's the first question, but what does it mean? Why is it there? What produced it? Your stromatolites are often silicified. Same problem. Right at the top of the Tsumeb subgroup, there's a silicified oolite. And in places, you have your dolomites, those dark chert veins in there. Are they silicified evaporite? And would be according to Murray Hitzman. Okay, where do we have mineralization? In the Kampveld, there's a little bit at the bottom, there's a little bit near the top. The main mineralization is the Geological formation where the ore shale is. In Zambia, you have Konkola and Mufulira, Mumwana, ore shale, Sentinel, Kolwezi. This unit is obviously not very thick. There's Frontier, Kamoa, Fishtai, Lonchi, Kipushi. Kipushi is the highest gold in that stratigraphic succession. We have our lead and zinc higher up between the two glacial units. Copwood is below the lowercase glacial unit. We have the Tsumet pipe and combat up here. We have Chuli at the base of the wood. That hasn't been found in Zambia yet. Brecciation diapirism, mainly the Congo crocodile. That's the rat, undeformed. It gradually gets broken up and brecciated. It forms a mono-mixed breccia initially, and finally a poly-mixed breccia in which you get large blocks of the mono-mixed breccia. What does that all mean? How does that take place? And you can actually see those breccias moving, becoming broken up into large blocks and apparently intruding. Brecciated rathill, brecciated rathill, broken rathill, brecciated rat siltstone, broken rathill. And there are two phases of breccia. There's a polylithic breccia 1 and polylithic breccia 2. It's a mess. And that's what the polymic breccia looks like. It's present in diapirs that weather easily, so it outcrops poorly. So a lot of that has been missed in earlier years. But what you get in there is our CMN, one of the units I was showing you from Congo copper belt with chalcopyrite. There's the SD with carolite. So what that is telling us that the mineralization in this case is early, before that brecciation takes place. And before the diapirism takes place. That's when most of your evaporites are salt, and you actually get real salt diapirs that carry these big blocks, mineralized blocks up within. You'll get it intruding sideways, and you'll even get salt, what's interpreted by Murray and others as salt glaciers flowing on top of the surface at that time. That's been interpreted by other people in a different way. What you have your fold geometry in the Congo copper belt. You have broad, rounded synforms and pinched, dismembered, antiformal crusts. Anticlines commonly occupied by megabreccia with large blocks, and they're up to a kilometer or more than a kilometer in size, in an argillaceous, sometimes talc-rich matrix. The folded sequence may be detached from rocks below. You can see that would be the lower Rhone down here, faults. That's a typical salt, those typical salt diapirs from the Gulf of Mexico. Look how similar that looks. Broad synclines with sharp anticlines. And the breccias intruding upwards through the sequence. And a major detachment, basically at the top, about the top of the lower Rhone. And from the stratigraphy in the succession in Zambia, the facies changes and thickness changes are suggesting that salt diapirism is starting while those units are being deposited. Finally, once the diaper has intruded, the salt gets dissolved out, leaving you a big cavity, and that's where the Kundalumbu is deposited. That's not too unlike the Morden of Namibia. Okay, the summary. That's the basement. Just white on the outside is the rectangular succession. Look where almost all the mineral deposits are there. Just above the basement. Just above the basement. That one in there is a porphyry copper, and somewhere else there is another porphyry copper. Don't know what that means. And the detailed work on the Zambian copper belt provides information on where you might find, or you do find, this mineralization. You need faults, You need stratigraphic boundaries, you need reductants, and pinch-outs focusing brine flow and the location of ore bodies. So there, your faults cutting through your source bed, the red beds, for the metals, coming through, and where you have reductants on either side of your fault, where you have the fluid flow, that's where the metals start to drop out, and they will drop out even above the top of the fault. You also play the game of petroleum geology, where you have the stratigraphic pinch-outs, you have stratigraphic tracks, you can move hydrocarbons, you can move sour gases. So you can get your ore bodies where you have those pinch-outs, and on top of where you have those pinch-outs. That's just the same thing in deformed state. Okay. Deposit classification. Now initially all these things were called red beds, but they are different. Starting at the bottom, your typical red bed type. Lufilian is one, the Kalahari copper belt is another. You have continental red bed conglomerates, sandstones, marcoses, with stacked into beds of carbonaceous argillite. Those are your ore zones. You also have vein type, which is Kansanshi, Fishtail, Frontier, Wanshi. The other ones are the Kupferschiefer type. And most of the copper belt deposits are Kupferschiefer type. They're marginal marine, possibly interfingering continental sediments, or large-scale saline lacustrine environments. You have, and this is key, basal red beds. That's your source of metals. Overlain by organic-rich argillates, right? Ozone, your reductants. But you can have different reductants, and those are overlain by a seal of evaporites and or carbonates. That's the combination that you seem to need. You start off with an intracratonic basin. Source of metals, red beds. Source of sulfur, gypsum, and pyrite, organic matter. So various sources of sulfur. Transporting medium, residual oxidizing high chlorine brines, up to 55 weight% in ACL. That will carry 100 ppm copper. 100 ppm copper is not going to give you a mineral. So what do you need? You need significant and prolonged fluid flow. How do you get that? You've got to have, first of all, a chemical trap, organic rich argillites, algal carbonates, mobile hydrocarbons. You need structural traps, pinch-outs, anti-traps. You need a heat pump, burial, intrusives, metamorphism. That's not always obvious. You need redox change to deposit the metals, reduction of an initially hematite stable ore fluid, and you need a seal, capping evaporites and or carbonates. That's what you need. The Central African copper belt, probably a closed hydrothermal system with long-lived and repeated circulation of brines below the sealing cap of evaporite and carbonate. That is key, a long-lived repeated circulation. Most deposits are stratibound, some cross-cutting. Most deposits are laterally extensive, in other words, a Kupferschiefer type. Kolwezi, Kamoa, Konkola are above the red beds. Lufilian is red bed type, it's within the red beds, producing units within the red beds. Mineralization from early diapirism to late tectonic and metamorphic, covering a period of 370 million years. Mineralization from the base of the Rhone to the base of the Grand Conglomerate, that is Kamoa. 90% in the Rhone, in other words, below the Grand Conglomerate. Deposition where there was in situ organic matter or migrated hydrocarbons. Fluid temperatures below 125 degrees C or greater than 300, and for the syn-metamorphic deposits, 400 to 550 degrees C. Okay, Zambian copper belt. Argillite hosted. Those deposits, Konkola, Mchenga, Kana, Ndola, Luancha. Strike length of up to 12 kilometers, very much kupferschiefer type, 70% of all deposits. Aronite hosted, Mufulera, Mchenga, you've got both in Mchenga, you also have the sandstones in Mchenga, Chingola, Ngweshi, Chibaluma, disseminated, often in sour gas trap sites, 30% of all deposits. Intense alteration. The alteration is not a guide to mineralization, but intensity of alteration is an indication of prospectivity. It helps. Alteration sequence. First you get calcium, magnesium, sodium, potassium, then potassic in the form of potassium feldspar, biotite, ceresite, magnesium, magnesite, phlogiston, talc, magnesium chloride, silicification, sodic, albite, scapolite, ferroindolite. The Zambian copper belt, mainly potassic alteration, Congo copper belt, mainly Mg and silica alteration. And that's where the silica is coming in. Northwest province, Mg and silica in depth, but sodic alteration higher up. Okay, Tavi group, the way forward from Namibia and the Tavi group. What do we have? We've got basal red beds, about 1 kilometre thick. In the southern margin zone, those red beds can be 6 kilometres thick and some of them are half dry. Lots of source rocks. We have syn-rep faulting. We've got half gravels. We have later faulting. We have antiforms and basement highs. We have reducing horizons. We have evidence of organic activity, black shales, stromatolites, albolamanites. We have evidence of hydrocarbons, bitumen clots, gas fenestrate. We have interbedded sandstone horizons. We have some evaporites, evidence of former evaporites. We have carbonates that could act as seals. We have many lateral facies changes and pinch-outs. We have early disseminated mineralization, shear zones, veins, pipes, metamorphic fluids. We have some alteration, calcic and magnesium. What we do not have is large-scale alteration, evidence of diapirism, but that's not a problem. The Kalkfeld mineralization is of the kupferschiefer type, and the kupferschiefer has no large-scale alteration. So we're not doing too badly there. We need what we're going to need. We're going to need detailed stratigraphic and structural mapping throughout the whole of the Tavi group to help us locate faults within and bounding the Nosset, even under the carbonate cover. Faults that extend into the carbonate cover, fault controlled facies changes, lateral or vertical facies changes indicative of reducing horizons, particularly recessive phyllite horizons, facies changes and pinch-outs into antiforms in basement and Nosset highs, evidence of the former presence of evaporites, organic carbon, hydrocarbons, cross-cutting breccias, would they be solution collapse breccias or diapiric, evidence of mineralization, alteration, could be very subtle the alteration. And what we're going to need lots of people mapping the Tavi, say a 50,000 sheet each, carbonated sediment to find all those features. We've got to find red beds, not too bad with that. We've got to find out conduits for the solution. And we've got to find where they went. The facies changes ought to tell us. We've got to find where we had reductions. So I think giving everybody an 50,000 sheet, we've got lots of MSc PhD projects ahead of us. But that is providing the baseline, the foundation for exploration to take forward. Thank you.